All right, I'd like to welcome you to What Physicists Do today. As you might notice, we're not in our normal location because of the drama over at Darwin Hall. We hope everything is all right, and certainly people got out peaceably. But here we are in the warm confines of the Schultz Information Sciences, the library. So I'm a little out of sorts. Okay. We have a wonderful talk today. I'm very excited. We have Dr. Rachael Beaton, who is a postdoctoral research associate at the Observatories of the Carnegie Institute for Science in Pasadena. In astronomy, we just call it Carnegie. But it's interesting. The full name is quite long, and it's this independent research venue. We were talking about how it's one of the few places in the world where your job is solely the astronomical research. And so this is a prestigious position that Rachael has. Her bachelor's and her PhD are from University of Virginia, where I found she worked with Steve Majeski, who I know from a short overlap at the University of Chicago. She's in the midst of a whirlwind schedule that has her visiting us on the heels of the resolving galaxies in the era of extremely large telescopes. GMT, Giant Magellan Telescope, sponsored conference with experts in the field looking at what the future in the era of the next generation of large telescopes, what the studies of galaxies and their assembly mechanisms will be. Her studies are of the stellar halos of galaxies to understand their formations and to also study the properties of dark matter and their role in the assembly of galaxies. And parts of her studies have to do with the cosmological distance ladder, a very important way in which we can know distances from here to the far edge of the universe. She has led major aspects of imaging campaigns to study these galaxies, and later this month she will be interacting with the public at the White House Star Party in DC. Very exciting thing to do. Let's give a warm welcome to Dr. Rachael Beaton.
Yes, so I study stellar halos, and I did the subtitle The Galactic Wild West because I think in a couple of weeks, or maybe even next week, you're having someone talk about the centers of galaxies, and they made this connection to the bustling centers of cities and things like that. So out in the halos of galaxies, things are very different, in much of the same way as a city like New York is very different from the 1800s Wild West, where there were outlaws and other strange things going on. There was no global sort of political structure. And I wanted to start with this picture because this gives you an example of the kinds of things that I do. So this is a big galaxy, like the Milky Way, a disk galaxy with spiral arms, a very normal vanilla cookie cutter galaxy, except that it has a companion here and a companion here. These are smaller galaxies that we call dwarf galaxies that are actually embedded within this galaxy's dark matter halo, which is a huge extent, and I'll show you exactly how big in the future. And these galaxies are orbiting the parent, and as they orbit the parent, they're actually being cannibalized. They're being ripped apart by their parent, by another galaxy, and eaten. Meaning that this black stuff here are all stellar debris, stars, that are getting ripped off of this baby galaxy as it circles its parent, and will become part of the bigger galaxy eventually. And there's other interesting things going on here, because this actual bit of debris is an even smaller galaxy that this galaxy has just eaten. And some of this debris is actually forming stars and forming other interesting things that you don't normally see in the outskirts of galaxies. So the outskirts, the very, very outskirts of galaxies, so everything you traditionally think about a galaxy is actually embedded right here. All of this other stuff, there's amazing information in here that we actually use to understand dark matter, because these regions are dominated by dark matter. Okay. So as a word of introduction, this is a light map of the United States. We're somewhere in here, I think. I actually grew up in this one last bit of dark on the East Coast. And so where I grew up, when I'm driving home to visit, unlike when I live in LA right now, I can actually look out the window and see more stars just out of the car window, gradually looking out the car window, than you can actually see pretty much on a large portion of the area in which you live. So astronomy has been something that's always motivated me because it was right there in my backyard. And it's still there in your backyard, you just can't see it all the time. And so that's why I eventually became an astronomer, and it's been a long road through graduate school and now at my postdoc. But that's just my perspective, is I think the skies are fascinating and I wanted to learn more about it, and that's what set me on this journey. But to start talking about why studying stellar halos are important, I want to go back to the beginning, which is the beginning of trying to map the universe. So this is a map of our galaxy made by William Herschel in the late 19th century, where the sun is here, and what he's done is he's actually gone out and he's counted all the stars along different directions in the night sky. And so the galaxy, as he's drawn it, looks a lot like a pancake. And the galaxy actually is a pancake. It's very flat and disc-like. And from inside, if you think about putting yourself inside of a flat circular structure, or a frisbee if you want, and you look around, when you look at the galaxy, you're actually just seeing it edge on as you span around. So that's what he's seeing. He's seeing this edge-on galaxy. And when he looks in different directions, he's actually learning something quite important, even though this is a very simple way to make a map. First of all, the galaxy is longer in one direction than the other. That tells you that the sun isn't at the center, it's somewhere offset. And as we look up and as we look down, we see similar numbers of stars. So that gets back to that, we're somewhere in the middle of the pancake, right? We see the same number of stars above and below. Turns out this way is towards the galactic center, and he has this huge region of obscuration, because that's the bustling center of our galaxy, which is full of gas and dust and all sorts of other things that are blocking our view of what's behind it. So this map, while very rudimentary at some level, and quantitatively not the best picture of our galaxy, was qualitatively right in that it got the overall structure of our galaxy pretty good for 1887, in a telescope in William Herschel's backyard, effectively. So at that time, we just knew about our galaxy, and one of the biggest questions in astronomy was, is our galaxy everything, or is there something outside of our galaxy? And this was the foundation of the Curtis-Shapley debate, so an entire debate between two scientists about whether our galaxy was everything, and so everything we see in the night sky, including these galaxies. So this is actually, we know this now to be the Andromeda galaxy, which is external to ours. But at the time, they just saw this from the ground, and it looked like a nebula, and it could either be in our galaxy or another galaxy far away. And so one of the key pieces of information, so this was actually at the Carnegie Observatories, was when Edwin Hubble found a variable star. Actually, where is it? Is it this one? No, but what?
It says VAR.
Yeah, so this is where he wrote on the plate VAR. Oh, it's this guy. You can't even see it on the screen. Sorry. So back in those days, you took plates on glass was your film, and the astronomers actually wrote on them when they were doing their science. And what Edwin Hubble found a variable star in Andromeda. It's a special type of star, and you'll have a talk later in the semester about someone who exclusively studies variable stars, and she'll give you all the fun stuff you can do with them. But the basic thing is that this variable star lets us actually get the distance to Andromeda. And to some degree, when Hubble finished all of his work, and he always looks sort of grumpy in his image, so here's one of his galaxy images there. It let him actually find out that either our galaxy had to be exceptionally large, which we didn't think, or that these were probably external systems like our own. So effectively, the universe doubles in size. We know that there are at least two separate galaxies, although this wasn't definitive proof. So that's why I have a caveat here. But this was a good clue. And Hubble wasn't done actually discovering things that changed the way we thought about the universe. Here he is actually with Albert Einstein when Albert Einstein was visiting Pasadena. And Hubble actually went out and observed the recessional velocities of galaxies, meaning that he looks at a galaxy, he sees certain spectral features, so certain line emission from stars or gas, and he can use the Doppler shift to measure how fast those things are moving from our perspective at the sun. And what he observed was things seem to be always moving away from us, which means everything's moving away from itself. And when he had some information about distances, he actually noticed that things were actually moving away proportional to distance, which is a little bit of a tricky concept to put in mind. So the way to think about it is a piece of bread, and you have raisins or chocolate chips or something in the bread, and that's us there. So as the bread is expanding, or as the bread is cooking, it will expand, and the other chocolate chips are always going to move away from you. And so this this observation actually told us that the universe as a whole is expanding. It's filled with galaxies that are all moving away from each other. And Einstein set about trying to describe that. And I'm not going to talk about that, but there's a piece of the puzzle. And I also want to point out this was an accidental discovery. He didn't go out to find it, right? He just noticed it while he was doing another program. So we've gone from just being able to map our galaxy to now knowing that our galaxy is one of many galaxies, and that the universe is this huge structure that's expanding. And this happened over a time span of only about 40 years. But we weren't done. In the 1940s or 1950s? 60s? Wow, I'm really off today. Two not quite astronomers, they were engineers, I think technically, working at Bell Labs at Penzias and Wilson, we're out working on this piece of machinery here, which is a telescope in the same way that you think about an optical telescope, but for radio waves. And what they were trying to do was figure out a way to do long-distance communication very effectively. And for that, you want to use radio waves because they have a long wavelength, and so they're a little bit, if you think about optical light, clouds can obscure the optical light. Radio light isn't obscured by things that are quite so small as particles in a cloud. So they were trying to use this as long-distance communication, and they were measuring signals, and they had to know their backgrounds very carefully. So they were trying to figure out what else was out there that might interfere. And it's a pretty interesting story because they kept, when they pointed towards the galaxy or towards the sun, they saw a lot of emission. And like, okay, so that's the galaxy or the sun. But when they pointed to other directions, there was always this very low signal in their data, very low, and it was everywhere. So they figured it was a systematic, or something that's everywhere, and they were looking at the antenna, and they realized that pigeons were actually living in the antenna at times. And so they actually were they were pondering the electromagnetic properties of pigeon excrement and whether or not that could be causing their problem. Because they're looking at it with the same view. And after however long it took them to prove that this wasn't the case, what they'd actually found is what we call now the cosmic microwave background, which is the radiation or the energy left over from the very early universe, from the Big Bang. So if we remember that the universe is expanding, going in different circles was how the universe could be expanding. And one easy model is that everything started together very early in time and has been expanding because of some unknown mechanism, which we call the Big Bang. And so this microwave background is actually the energy that was left over from that original explosion. Or that's a way to think about it. Again, not looking for this, but they found it. So now we've gone from just trying to decide if our galaxy is one in many galaxies or the whole universe, to now being able to actually observe the very earliest times of our universe from Earth, which is a pretty big jump in a very small amount of time. Another interesting discovery, again, not an intentional discovery, was that when we go to look at galaxies and we apply physics about how we think these galaxies are moving, we can see its luminous mass and we can calculate how we think those galaxies should be moving, how we think objects can be moving. But when we measure it, we actually get a pretty large difference. And this was it's not the only evidence that there was some sort of dark matter or matter that we couldn't see. But it was one of the ones that people really perked up and started listening to. And this was done by Vera Rubin, also at Carnegie Observatories. And it looks like she's using a microscope, but what she's doing is looking at plates of galaxies, so here's some here, and making measurements through something that would enlarge the plates. And I like that picture because it shows how different things are now. Now we look at images on a computer, but back then we used a lot of complicated material. So what she found is that if we look out into the universe and are trying to count the amount of matter there, we can't just use the luminous sources, right? There's more there. And this was very important discovery. So now we know that the light, so we can see the earliest parts of the universe, but we can't see everything in the universe, which is kind of a bummer. And 20 years later, this one was pretty recent. This is a fairly recent discovery. Adam Rees was observing supernovae that were expanding away from us, and he was actually able to measure that the universe was not only expanding, but accelerating. So at early times in the universe, when he looked very far away, the universe was expanding in a different way than it is now. And the way to think about that in our bread analogy is that over time there's been a different amount of leavening or amount of yeast or baking soda or whatever in the bread. So something about the universe has been changing over time that we need to go measure. And if we think about leavening as pushing things out, we call this dark energy. We already had dark matter, so we'll call this dark energy because it's behaving differently than dark matter. And so this was in the late 1990s. So again, a serendipitous discovery. And we've gone in a span of 100 years, we've gone completely different scale of the universe. And so many people, not just one person finding something serendipitously, worked very hard to create an incredible map of the universe at early times. And from these earlier discoveries, we know not only do we have light coming from galaxies, do we have matter, like you and I, we have dark matter and dark energy. And so they take this map of the temperature of the cosmic microwave background, and each one of these things are little fluctuations. So parts of this are slightly cooler and parts of this are slightly warmer, because we're measuring a temperature of the universe, of its energy. And what it's really tracing us, if we remember that energy, E equals mc squared, so that energy and matter are very similar, is it's giving us the distribution of mass in the early universe. And so using a set of complex tools, they analyzed this map of the early universe, and were able to model it to show that it seems like almost 74% of the energy in the universe is actually in dark energy, so something that we can't see and we only were able to infer fairly recently. 22% is in dark matter, so that's stuff that we find in the outer parts of galaxies. And only 4%, here it says atoms, but another word for that would be baryons, which is matter like you, me, trees, sidewalks, etc. So of the stuff that we can go out and study and probe, and even the things that we interact with on a daily basis, it's only about 4% of the universe. Another way to go about this, or to look for these same things, is to compare the way the universe would look if we take that map. Hold on, how do I go back? If we take this map as a starting point, and we let it accelerate and expand, what does the distribution of matter look like? And so a lot of people over the past 20 years have been surveying galaxies and trying to figure, they know using their recession velocities, so how fast they're moving away, we can figure out to a good degree where they are, and then we just plot them on the sky. And so here are two distributions. This is the theoretical prediction about how galaxies should be mapped out in a universe in a box. And here are the observations from a field survey in the southern hemisphere and from the Sloan Digital Sky Survey, which you may have heard about. And basically we see that if we, taking this view of the universe, this fairly simplistic pie chart, and the distribution of matter at early times, and a lot of physics in a box, we can actually predict the large-scale structure of the universe in terms of where the galaxies are, where the light is that we can study to a pretty high degree. And I really like this graphic to show how these different spheres are intersecting. So here's us here, and we're looking out. And with the Sloan Digital Sky Survey and other programs, we can survey a volume going fairly far back into the history of the universe and map out where the galaxies are, where the luminous matter is, and using various relationships between how much luminous matter we expect a dark matter halo to have, actually map all of the dark matter and the luminous matter. And we're reaching out towards the cosmic microwave background, which is of the universe at very early times. And what happens between here and here is something that we're still trying to figure out, although we have some really good guesses. So a lot of the next generation facilities that I was talking about, that I was at a conference about, are actually probing trying to probe into this era of time. And there's ways that we can do it with local galaxies as well, which is what I'm going to talk about. So with computer simulations, this background is sort of a universe in the box. And we can zoom into these different structures. So this is zooming into sort of the scale of a galaxy cluster or a galaxy group. And then we zoom into a galaxy's halo, which is, this is probably a little bit bigger than a galaxy's halo. And then into an original galaxy, we're actually seeing the structure of dark matter. This is all run using dark matter, which has physics that are fairly straightforward to put into a computer simulation. And so I'm going to zoom in on a single galaxy and show you what is interesting about that. So this is a single galaxy from a simulation called Via Lactea, which is Milky Way in Latin. And the center of our galaxy is here. And this is the expanse of what we'll call the halo, which I'll define observationally later. So this is the theoretical, what we call the halo. And each one of these little dots is the remnant of a smaller dark matter halo, or a smaller galaxy to some extent, that has been eaten by this bigger galaxy. So what the dark matter simulations, which are founded in our global structure of what the universe is doing, tell us that galaxies are filled with the remnants of the things that they've consumed over their lifetimes, and B, that a major phase of how galaxies form and evolve is actually by eating smaller pieces, smaller galaxies. And we call this hierarchical formation, where little galaxies are coming together to make big galaxies over time. Unfortunately, we actually can't go out and observe dark matter because it's dark. So we have to think a little bit more cleverly about what we're doing. So if we take that simulation, we actually know all these different pieces, all these smaller galaxies that went into the bigger one. And if we put representative galaxies on top of them, we almost paint it on that model, we can actually build up a simulation that looks like this, that was done by James Bullock and Katherine Johnston. So this is just taking very simple models of galaxies and having them be stripped or eaten by their parent over time and saying, what does it look like? Because we can observe stars. So we really want to know what the stars look like. And for those of you who do observe or think about observing terms, the top bar, this color scale, is actually giving you surface brightness. So that's the amount of light over a square on the sky, which is spanning from 23rd magnitude in the very center down to 30th magnitude is about where the projector is going to cut out. And the Sloan Digital Sky Survey is only going to be able to sample to about here on this map over the sky. So a lot of the things that we're really interested in learning about, in probing of how these galaxies come together to make the bigger galaxy, is actually relatively invisible to us right now. So we can also break this down into other things. Wow, that's not showing up. Okay, well this image has disappeared, so I can't tell you what that looks like. But if we look at these overdense regions, we often call those satellite galaxies. Those look like galaxies that I showed you at the beginning that are still relatively intact. And these are things that are going to accrete in the future. These large structures of material are what we call tidal streams, or tidal debris. And those are things that are ongoing. Those are the stars that have been pulled off, but we can still identify them as being in the process of being accreted. And then we also see regions where we can't actually see a difference between the different structures. And we call that the smooth halo, or that's what's been accreted, and we can no longer piece it out we can no longer separate it into individual parts. So that's the past accretions. So in the outer part of the halo, I said it was the Wild West. It's very quiet out there. These objects are on these long orbits that take a very long time to circle. And because of that, we say they have a long dynamical timescale. It means that they don't always sense the other things that are going on in the galaxy because they're so far away. And each one of these different phases of accretion is actually preserved for a very long time in the halo. So these are fossils of how the galaxy came to be. And if we go out and find them, we can actually learn how the galaxy was put together, and we can test some of the very specific predictions of individual galaxy formation, like do we see enough satellites to make that model that I showed you to begin with. And we can do some other things as well. But there's more information actually in the shapes that these things make. There's 3 canonical shapes. This is a great circle, meaning that it traces a great arc on the sky or from the inner part of the galaxy. This is what we call a shell, plume, or cloud. It depends on how you look at it from inside or outside. But basically, it's an overdense region. And then you also have things that are mixed, which actually don't have a clear morphology. And still bound objects, so galaxies that are still galaxies. And if you look at the orbital energy versus the time since it started to get eaten by its parent, these different morphologies actually tell you a little bit about the orbits of the things coming into the parent, which is very interesting for large-scale galaxy simulations, since it appears, if you remember, we call it the cosmic web, it appears that certain things come in on filaments in preferred directions. So there should be certain orbital distributions in the debris that we're able to find. So there's more, it's more than just counting and making a picture. There's some physics that we can use. And the way that we're going to go out and find these tidal debris and learn about them is to use the Hertzberg-Russell diagram. The Hertzberg-Russell diagram is a story in astronomy when many people were working on the same thing, and finally Hertzberg and Russell sort of put it into made sense of all these things that they were working on. And what it is a map of the temperature of a star, which is what we call its spectral type, versus its absolute luminosity, or its absolute magnitude is what we actually observe. And stars actually separate by type, and they separate by size to first order in this diagram. So this is what we call the main sequence, because this is where stars spend most of their life, hence main. And these are what we call evolved stars, which have come off the main sequence and are going into later phases of their life. Most stars, and most of the stars that I'm going to talk about, live all of their lives in this sort of area. And only the most massive stars actually go through these things. So Hertzberg actually found this in 1905 and 1907 using samples of data that had very similar spectral types, but had very different brightnesses when they were able to measure their distances. And he published it in an obscure journal about photochemistry. And no one figured that out for a very long time, which is a funny story about sort of stumbling into different things. It was actually only cited by another astronomer in another paper that he had found this so early on. And Henry Norris Russell actually made a similar discovery about stars seeming to have different intrinsic luminosities, or intrinsic brightnesses, actually using observations of variable stars to constrain the distances and masses of different stars. And imagine if they had been talking to each other early in this experience, how much more quickly things would have been sorted out. So our major tool for understanding stars is using the properties of where stars fall in color, temperature, and luminosity space. And I'll call this a color magnitude diagram because that's what we actually observe. We observe color and magnitude, not temperature and luminosity. All right. Another neat thing about this color magnitude diagram is that groups of stars of different ages, and this horrible to read legend is supposed to be showing that, actually take on different parts of this diagram. So the youngest stars are over here, and then as systems get older and older, they tend to be over there. So by looking at an ensemble of stars and comparing it to some of these fiducial sequences, we can actually learn a lot about the star system. So in the halos of galaxies, we're primarily seeing older stars. So here is the main sequence where it's turning off and forming the giant branch. And so a lot of what we see in the halos of galaxies are just this particular portion. But if we could see multiple ages and multiple different populations, it would look a lot more interesting. So to go from that canonical picture, which is all the nearby stars, to what we actually see in external systems, you have to do a little bit of extrapolation, a little bit of work. And so when we're going out to study halos, and I'm primarily going to talk about external halos, the question is, why don't we do this kind of study in the Milky Way? And this is a picture of the Milky Way edge-on, so our view of the Milky Way from inside of the pancake. And there's the galactic center. and then the disk of our galaxy stretches out all across the night sky. This is actually in Death Valley. And the reason that we don't use the Milky Way as our primary vehicle is because it's literally everywhere. The halo is everywhere, is all of this part of the sky. And so to study our halo, and the Milky Way halo, in a very systematic way, we have to have instrumentation in both hemispheres. We have to have astronomers in both hemispheres. And that is really hard to do right now. And there are several projects that are pushing this forward. So we actually, and there's more. So not only is our galaxy's halo everywhere, I actually am going to tell you what the halo is now for the first time. This is a canonical picture of what galaxies look like. So here's the bulge, the disk, the thin and the thick disk, and then globular clusters that you see in the halo. And this is pulled from the Encyclopedia of Astronomy. And it's pointing to the halo here. And that's okay, except the sizes are a little off. This is the actual halo. This orange circle is the size of the halo. This is that picture of the galaxy that we saw. And to span, there's about 40 kiloparsecs across for the Milky Way. And the halo of our galaxy contains about 7 of those. It's at 300 kiloparsecs. Okay. The halo is big, is the other problem. So it's all over the sky in the Milky Way, and it's incredibly big. And what does this mean? So if we were to go out and look at a single galaxy, this is a dwarf galaxy called Leoline. Its name only means that it's in the Leo constellation. Here's the red giant branch that I showed you before. Okay. And we can see that, because all of those stars are at a single distance. So they have a single apparent magnitude. The distance modulus is the same. So the difference between its absolute magnitude and apparent magnitude, things that are the same luminosity but further away are going to be fainter. But since we have a number of stars at one location, we actually see its signature quite well. And this is at the very edge of the halo. If we look at all the stars outside of the physical extent of the galaxy, we're actually looking at the halo stars. And these same stars that we were trying to study now span this huge range in distance. So this is the halo that we would try to study. And it's incredibly hard to pick stars out of there and to make sense of it. So we need to look at systems more like Leo 1 that appear very simply in the color magnitude diagram. And other things going on is that we actually have, this is actually fainter stars in the disk that are actually at the same magnitudes. So trying to study our halo, the Milky Way halo, is really, really hard and almost impossible to do. And so Andromeda, our nearest neighbor, the same galaxy that Hubble originally found his variable star in, is a little bit easier to study. So this is an image of the night sky, which really doesn't show up well on the star projector. But if you went outside and looked at M31, you might be able to see a faint smudge. And this is just an all-sky view of the Andromeda galaxy, which fits in this potential sphere. And this is the same image I showed you before for the Milky Way. Here is its halo on the sky. And the moon might also be, there should be a circle showing the size of the moon, but basically the moon is about that big on this diagram. So the M31 halo is still really large on the sky, but it's much easier to study than the Milky Way's halo, which is the entire sky. And since the Milky Way is further away from us, all of its stars are going to show up at effectively a common distance. There's a little bit of spread for distance, which means that we can pick out its stellar sequence in the color magnitude diagram much more easy. And this was the motivation for a survey that I did as an undergraduate and a graduate student called SPLASH, which stands for the Spectroscopic and Photometric Landscape of the Andromeda Stellar Halo, which is an incredibly connived acronym, but we just call it SPLASH. And what we did was we actually looked at specific regions in the Andromeda galaxy. So each one of those red boxes is a field. And like I said, it's a reasonable area to study, far less line of sight depth to smear out those features. But the con is that we actually have to look through our own Milky Way to do this. So just to orient you, here's the background of your Mac computer. It fits in that box right there. So we're going well far away from M31. And for the observers, this spans 14 degrees on the sky, and we're going out to about 2/3 of where we think the dark matter halo actually ends from theory. We don't actually know because we can't observe the edges of the halos directly. So this was a pretty amazing survey. It took us 9 observing seasons to get the photometry, and then we followed it up with spectroscopy, where we could actually get the radial velocities of the stars and learn about how they're moving. And we have about 35,000 spectra taken with Keck plus Deimos, which is mainly for the observers in the room. This was a Herculean effort. And the question should be why, so I have this filled area map on the background, which is from a different survey, but why are we just using these individual boxes? And the answer is that we have to worry about the foreground contamination from the fainter dwarfs that are now at the same magnitudes as our target red giants. So this is a histogram showing you colors of stars and the numbers of stars in a field that's very close to the Milky Way and in a field that's very far away from the Milky Way. So our galaxy's disk is actually towards that direction. Yeah. And here are the dwarfs. So you can see this is the signal that we want, and it's dwarf. It's hidden completely by the foreground. As we move to the other side of the Andromeda galaxy, it's a little bit better, but the signal is still pretty strong. And so this is actually a dwarf galaxy, like Leo 1 that I showed you earlier. And I use this as a comparison because it's really easy to pick out the target stars. In the halo of M31, it's a little bit more diffuse. Okay. And to show this in a different way, which I think is even more illustrative, this is actually one image on the sky. It happens to be where Andromeda 7 is located, which is just a dwarf galaxy, the 7th dwarf galaxy found in Andromeda. And it's here. Does anyone see a galaxy? Yeah, you probably are going to find it too.
Fuzzy bit. There you go.
Yeah.
Is that it?
Yeah, that's it. That's Andromeda 7. It is incredibly hard to find these things. So the technique that we use is actually a star-by-star way to say, is this galaxy a dwarf or a giant? And what we do is we use differences in the spectra, or in the light distribution as a function of wavelength, between dwarfs and giants. Dwarf stars are exactly what they sound like. They're small, they're compact, they have higher gravity, surface gravity. Giant stars are bigger, they're giant, they're fluffy, they have lower surface gravity. And what we see is that this feature in the spectrum is actually dependent on whether or not you're looking at a dwarf here, so it's very deep, or a giant, so it's not very deep. And so in the same way that we use color to measure temperature, so a color at something in a hotter wavelength, not a hotter wavelength, but the same way that we can actually build a temperature-sensitive index, we can also build a surface gravity-sensitive index. And that's what this plot is showing. And here are the dwarf stars confirmed with spectroscopy. And the giant candidates are here. And this is really important because here, this is actually a smaller galaxy than Andromeda 7. So here's the distribution of all of the stars. And here's its color magnitude diagram. The RGB, the red giant branch is right here. I know where it is because I look at these all day long. If I select it here, this is the distribution of stars. So just by selecting on the RGB, we beat down the surface brightness quite much. But if we use this surface gravity sensitive index, where this is our surface gravity metric, this is our color metric, we can actually circle the giants, just like in the other diagram, and our backgrounds actually go down by a factor of 2. Which means we can go in and follow up these stars and study their structure, the structure of their parent galaxy, the dwarf galaxy in this case, very well. And yeah.
Can you go back? So it's confused. You know, you have these two populations of stars, dwarfs in our own halo, right? And these. What's the total fraction? I'm looking at that one on the left and saying, you're trying to pick out what, only 1 out of 10 stars in general. I mean, in the vast region, but in the region of overlap. I mean, is it 1 out of, if you use both sets of stars, you'd be completely lost as to knowing anything about the properties of those stars.
Right. So if I just picked a star at random out of this field, I'm probably 20 times more likely to pick a star in our galaxy than an actual M31 star, or Andromeda star. And that means if I want to learn about Andromeda, I have an uncertainty of 20 to 1 about whether or not I'm picking the right star. So most people just draw a box here, and that's okay. It does a decent job. You see that it improves quite a bit. But the problem is that we're going to such low numbers of stars in this structure that even this level of uncertainty, where I have, it's actually more like 1 in 3 or 1 in 5 in certain parts of the Andromeda halo, that's still not enough for me to go to the Keck telescope and use one of the biggest telescopes in the world to try and get follow-up data. It's also not enough for me to derive the overall structure of that galaxy. So we add an additional layer where we do this selection, and it's quite expensive up front, but it means that back-end follow-up and the back-end science that we do is actually far less subject to picking the wrong type of star. So, yeah, that's what I was trying to get to. Didn't quite get to. But this is really important, and so my entire thesis was doing this over and over and over and over again. But I think we've done a lot of science. So one of the things that we did with this particular project, which is pretty neat, so here's the model I showed you before, and it's color-coded by the number of stars in some area bin. And we've actually been able to plot from the center part of the galaxy, which is here, all the way out to its edge, very close to where we think the theoretical edge of this galaxy is, and to actually plot its structure. And this is the first time we've ever gone so far out into a galaxy, and it's actually the best global portrait that we have of what this stellar halo looks like. And so you can map here, this number is the surface brightness, so the number of stars per bit of area on the sky, to the colors here to show what we're actually able to get down to in these individual fields. So we're actually able to get to some of the most interesting parts of the structure and actually pick out these remnants, these fossils of the accretion history, because we can model this so well. And a large part of my thesis was actually, this actual plot is based on a smaller sample of our total galaxies, of our total area, and I actually pounded away right here to prove that that bit of the diagram is very robust. So that's at about a third of the way out into the halo. So we actually know not a ton about halos because this is the first time we've been able to do this. But I've been showing you this halo over and over again. It turns out that every single halo that we do in simulations or that we go out and observe with incredibly deep images is different. Okay? I call them special snowflakes. You'll notice that the inner parts are different, the outer parts are different. It's all, galaxies have an incredible amount of differences, just like people, or different areas on the globe. And we think, because these are models, we actually know what the difference is between this halo and between this galaxy and that galaxy. And it has to do with the number, the timing of, and the properties of the galaxies it eats to build up this distribution. Okay? We don't know exactly what's happening here. It's a good bet that this galaxy has only had one big interaction that had specific orbital properties, and this one has probably eaten many things to make all of this structure. But there could be other differences in here, in these galaxies, that have to do with when they formed in the history of the universe and things like that. So one thing that we're trying to do is using the SPLASH program that we did is trying to say, so these red giant stars we can actually probe in many, many galaxies. But the real difference is, like I said, not just the number of features, but the timing and the properties of the parent of the galaxy that it ate. And that's what's really important, which we can't actually get just by making these beautiful images, unfortunately. And this is a plot which is showing you the time that something accreted and what it looks like now. It's surface brightness that I keep talking about, the number of stars per area. And this is color coding by the properties of the parent, where each of the, I haven't shown you the color, the actual scaling because it's a quite nuanced thing, but the basic thing is that the red, the blue, and the yellow, and the black, and the diamonds all are different types of galaxies that fell in. And in this space, they inhabit some of the same areas. It's what we would say degenerate. I can't look at this feature and learn a lot about the galaxy that formed it. I can learn some things, but not at the level where we want to test why these halos look different. So here's another theory plot, but this is if I just break up the plot that you just saw and I just show you things that fell in 12 giga-years ago, which is almost to the beginning of the universe, about half of that time, and very recent. So only about 4 what's a good word for a giga-year? Billion, that's it, sorry. Billion years. And the thing is that these structures actually look very different because of the dynamics and how the debris over time eventually fluff out and form a coherent structure. I also show you that the chemistry of these objects is also very different. So other people that I work with that are very, very smart are measuring these types of things because this is really interesting for how we get the elements. But what I sit down and my colleagues, we're trying to come up with a way that we can get this number and attach it to a debris field that we see. And we're going to use Andromeda and this beautiful data set that we have of Andromeda as our test bed. Because ultimately what we want to do is look at any galaxy in the sky and try to infer this information and compare it to the models. Okay. This is a plot of the distance of a galaxy, a satellite galaxy, and its ability to form stars. Okay. So on this side of the plot are things that look like this, where these are individual stars. And it has no ability to form stars. That's what this line is basically saying. So that means these galaxies have no gas to form stars. Outside of our theoretical limit of the halo, which is here, so that 300 kiloparsec number I keep throwing around, we see different galaxies that have a high potential to form stars, and they look more like this, where these are actual star-forming regions. And you'll note here, you can see through this galaxy. It's pretty boring, and it's almost what we would call dead. So what we know about galaxies is that when they fall into their parent halo, when they start interacting with their parent, they lose their ability to form new stars reasonably quickly. There's some deviations from this rule. These are some galaxies that look like this. And you'll see that you can see through parts of this galaxy. It's dead in a sense. But in other parts, it actually has active star formation. And these galaxies are galaxies that we believe fell in very recently. And there's various reasons for that. So they've only been interacting with our parent for a very brief, with its parent for a very brief period of time. So if we can actually go in and age and figure out the ages, the youngest ages in a galaxy that's forming the halo, we actually have a very good estimate of when it fell in. And that's the number we need to make an accretion history.
Rachel?
Yeah.
Can you give me an idea about this? So the idea is I've got a dwarf spheroidal. I see it somewhere. This measurement on the left is just saying how, the left side of that screen is the things that are close into their parent galaxy.
Yeah, these are things that are within sort of a sphere of influence of
and
their
parent. And the up and down, the y-axis is star formation rate, so they're lower, and so they're dead and quenched.
They're dead. Quenching is one word.
Yeah, that's I shouldn't.
It's a very nuanced word. We get into arguments about that at conferences.
I'm sorry.
The main thing and the point that is happening is that the gas in a galaxy, and the reason why the inner parts of galaxies are so active, is that gas is sort of very sensitive to its gravitational environment in a way that stars are not. So the gas can sort of sense that it's passing into the halo, and it very quickly says, oh, I want to be a part of the parent galaxy. I want to jump in there because it's boring out here in the halo. Whereas the stars are a little bit more pragmatic and they follow a different orbit. They're less sensitive to a change from being, literally, from being here to here. And is that?
Yeah, so I mean,
Yeah.
I was getting to kind of that broad question. Is it it's the gas,
Oh.
you kind of use this word of the gas leaving, saying I want to jump ship and be part of the parent galaxy, and certainly that's part of the process. There's also part of this process, if it kicks into gear a lot of star formation, then you also change that ratio between the number of stars and the...
So an alternate approach is that this galaxy comes in and it says, I want to form a lot of stars, because now the gas is sensing that halo, and it forms a lot of stars very quickly, and it evacuates its gas. It blows it out. So that's an alternate approach.
Yeah, what's your mental model for this, or do you hold both of those in your head when you look at this, which is measurement of real things, right?
Yeah. So, sorry, some of these slides got a little out of order. These galaxies all have very enhanced star formation rates to some degree, not only compared to other galaxies that are in similar places in the halo, but compared to many galaxies in the field. So, you know, there's a lot of scatter here, so there's galaxies live in different places on this plot, but these galaxies are towards the higher end, or at least in the middle. But if you look at this region here is one of the most powerful star-forming regions in our local universe. So this galaxy is experiencing something quite dramatic, and we're not sure what's driving that. Because this particular galaxy has its own companion. So this is the Large Magellanic Cloud, and it has a friend called the Small Magellanic Cloud, and they're actually tumbling around each other as they're tumbling into the Milky Way. And so it makes it very hard to interpret this galaxy. Yeah.
Can you say that for every galaxy there is a parent galaxy that's eating it? Can you say that every galaxy has a parent?
Down to...
Then you can infer that something's eating everything?
Yeah, so except for the biggest galaxies in a galaxy cluster, pretty much every galaxy is moving towards a bigger galaxy in some sense, in the sort of cosmic sense of the universe.
Bigger galaxy, the galaxy cluster. So if you have a really big galaxy cluster, is something not eating it as well?
Well, so it turns out the bigger cluster is eating it, the cluster that's far away. So we live in a sort of a special region of the universe. It's just us and Andromeda. We're actually spiraling to each other. We're going into each other. In about 4 billion years, we will be one galaxy. But our neighborhood is actually moving quite significantly towards a galaxy cluster. So we will eventually merge with the next biggest thing. And that next biggest thing is actually bringing in stuff from other places too. We're on a filament going into a bigger thing that's over here. So on a certain scale, gravity wins and is pulling everything together. On a much larger scale, gravity's losing and everything's being pushed apart. That's the expansion of the universe. That's dark energy. So it's not an inaccurate way to think about it that everything's slowly being consumed by something else. On the scale of galaxies. On sort of a bigger scale, we're all moving away from each other. It's kind of a tricky thing. It's a nuanced thing to keep in your head. But most galaxies, to a certain mass limit, will be eaten by their host. So a lot of people spend a lot of time trying to find galaxies that aren't, or that are very far out, and their interactions are very separated, because those galaxies are what we can call almost natural galaxies that have had none of this interaction driving their lives. But if anything, if you sit on that galaxy for a really, really, really long time, you will start to see these things. We've not imaged galaxies deep enough. This is an image by an amateur, which is about 20 hours on a small telescope north of here. And there's no image that goes this deep. There's no other image that goes to this depth. and can pick up these really, really faint things. And we've only done this for a handful of galaxies. So whether or not, so it looks like part of this picture is that all galaxies are continually eating each other over and over and over again. And most of their mass or their structure is somehow driven by these interactions. But we still, there's other stuff going on too in this disk and other things too. And so one of the questions by building up a sample of things that we've probed very deeply or very carefully, and we build up these accretion histories, is to ask questions about the inner parts of galaxies and how their structure, their behavior, might be driven by these interactions as well.
Thank you, Rich. We kind of
yeah.
a little of your talk.
No,
question
it's fine.
Time, I think.
No, I mean this is I think we got to the science concept I want to get to, which is just that building these accretion histories is crucial if we want to understand how galaxies form, individual galaxies form, and understanding this diversity is really important because in these huge simulations, a lot of the global properties of galaxies look like they come out the same, but we see a lot of differences. And so we're at this intersection now where we're trying to understand what that means. And that's what the conference I was at before this was all about, is about doing the very detailed things that I'm doing in Andromeda on a master scale where we can actually start doing this physics. Okay, so I can stop there. That's the gist.
Well, did you want?
No. I promise. The point I wanted, you got at the point I wanted to make, just in a different way. It's just that, every galaxy seems to be eating other galaxies, and what does that tell us? And how does that impact the models? And how does that impact our view of the universe?
Well, let's thank the speaker.
I don't know if they call it stealth or dark matter, stealth energy, or whatever you call it, dark energy or dark matter. Is it on too large of a scale to have a lot of effect on these individual galaxies? Or is it affecting them? We just don't know how.
Okay, so let's see, how do I answer this? Let me go way back. Okay, so we think, this is if we could put on dark matter goggles, this is what every galaxy would look like to some degree. Okay, and these overdensities are chunks of dark matter that are sort of a unit together, and then there's also sort of a smooth thing going on as well. Not all of these things will have a galaxy associated with them that we can go out and observe with a telescope. Some of them have no stars whatsoever, and we call those stealth galaxies, or my colleague calls those stealth galaxies, which means we have no way to observe them. We don't know that they're there. This is a model, okay? They may not be there.
You just have to understand dark matter more to understand these.
There's two approaches. There's people who are looking for dark matter, the particle, say in the Large Hadronic Collider and other things like that. And there are those of us who are out mapping the universe. And so I'm a small scale mapper trying to look deep into individual galaxies. And there might be observational ways for us to see the effects of these things, because these all obey gravity, right? So if I go out and I very carefully map this structure and how it's moving, if hundreds of thousands of little things it's feeling the pull of hundreds of thousands of little things, if I do this carefully enough, I should be able to see that. So it will look fluffier or thinner or all that kind of stuff. But unfortunately, the models aren't detailed enough. The way we put galaxies, there's a lot of uncertainty about how we paint a galaxy onto this chunk of dark matter. So is it going to have 10,000 stars, 100,000 stars, etc.? That's called it's called the too big to fail problem. which is because there are some galaxies that are big enough that they should be well characterized by their dark matter profiles, but they don't match the things that we see in simulations. So the uncertainty really is in how I map this to this. So how do I paint stars onto this map? And that has a lot more to do with what's going on inside of galaxies than with the sort of structure of the universe itself. Yeah, so my colleague, the same colleague that came up with stealth galaxies, he's very good at this. He calls it putting the astrophysics onto the physics of dark matter. Which is a beautiful way to think about it, because we just can't. So what I'm trying to do is to come up with the ways that we can characterize this to understand where it came from in this picture. Which happens to have taken, a huge chunk of my life. It's really hard to do because these things are so very faint, which is why I spent all this time showing you all how hard it is to find these things. But this is where, this is awesome, right? And like 100 years ago, yeah. We thought our galaxy was a potato-shaped blob, and now we know that it might look like this if we could see it that way. Yeah.
So your subtext there says that prediction comes from the lambda CDM cosmological model.
Yes.
Have you modeled it? Have you redone the simulation using different models and assuming the background?
Yeah. So I don't do models. I observe. It just happens that I try to listen to what the models are telling me when I go plan my experiment. So this level of simulation, this is called the Millennium Run. There are people who go in and they tweak things and they see, for instance, they count these halos and they see how many change as they change different parts. So the lambda part in lambda CDM is the dark energy, and the CD, cold dark matter, CDM part, is all about the temperature of the ultimate dark matter particle. What it really means is how does it clump, and how many clumps does it make. So if you make dark matter a warmer particle, it doesn't clump as much, and it's puffier. So one way to get rid of, so this is called the missing satellites problem. We don't see 100,000 satellites like this would suggest. We only see about 100 of them, but we haven't surveyed the whole sky yet, so they could be there. So one way is to puff up the dark matter. Another way is to say, well, maybe the normal matter, like you and me, can communicate with the dark matter under certain conditions. And this is called feedback, and that's where the actual behavior of the gas can actually influence something about the dark matter, and that can puff up the dark matter. So there's sort of a bunch of different camps, but they're focused on making the dark matter a little bit puffier. We observers are actually just trying to see how many of these halos we can find galaxies in right now. So I think the theorists are a little bit ahead of us, but they're also trying to answer different questions. So we've gotten to the stage in theory where they can actually make galaxies in this, and those galaxies look both different and the same as the ones that we see. And so a lot of people are tweaking a lot of very detailed knobs, and it's a really interesting study. But in terms of counting dark matter halos, the observers are still working really, really hard. And so just in the past month, we've discovered, not me personally, but teams have discovered about another 12 to 15 satellites in a new survey in the southern hemisphere. So I would say the jury's not out observationally, the jury's not complete observationally about how many halos we have, but I do think this one actually gets down to Earth-sized dark matter halos, I think. That's probably, what? Solar mass-sized, or some of them even go smaller. And that, I think, is probably too small.
So that'd be the smallest blob of dark matter?
Yeah. Yeah. Yeah.
So halo observations then could really help narrow down with some different cosmological models. Like you can see how clumpy or not clumpy dark matter is.
Yeah, that's the idea. The idea is that if we go in and can measure these things incredibly carefully, we can actually predict, and this is actually a model as well, but it's looking at stars, but we can actually compare it to a detailed simulation, maybe, hopefully. I think it's definitely possible. And there's lots of different ways to go about it. Yeah.
I have a question. So you presented, well, a way to look at it by going into detail in single galaxies or single assemblies of these dark matter halos. While you were giving your talk, you showed some of the images of interactions. So we have that. We might have even a large number of interacting galaxies that are some assembly, some ratio. I'm just wondering about that field. When I think about that, you could constrain some of the lambda CDM models and how they vary in kind of, I would assume, kind of a statistical ensemble of saying how many times do they make, interactions that occur like this. I mean, you have all of these parameters. In fact, when you even on this where it's a single example, it has the, I think you called it a shock, or it might look like a bow shock or tails. Is there work, and if so, where would you point me to look at the work that would just sit counting streams, properties of streams of these sort of brighter end things to say, can those constrain the lambda CDM model?
Yeah, so in terms of the picture I've painted here, which is the Milky Way's formation and the types of satellites that form the Milky Way, in the next month I have a book chapter coming out on that, where it's a whole book on tidal streams, telling us everything that we know from the detailed streams in the Milky Way out to the extragalactic. And the answer is that there's actually very few surveys that go that have the proper amount of data for you to go in and count streams, like at this level. And a sort of disturbing thing is that most galaxies don't have a stream to a certain surface brightness limit, which this model and this set of models would predict that every galaxy should have a stream at some magnitudes per arc, some surface brightness, number of stars per area. And in the Sloan Digital Sky Survey, only 1 in 10 galaxies, no, it's even less than that. It's only 1 in 20 galaxies that are of the appropriate scale to actually apply this algorithm seem to have any debris whatsoever. So at this mass scale, there's a lot of work left to be done, and it's a difficult problem because you almost, computer algorithms are not very good at picking out, compared to the human eye, at picking out patterns. So it's something that just needs a lot of man hours to actually look at every single galaxy. In terms of larger samples, so looking at, so the mass ratio between this parent galaxy and this guy would be less than 1 to 10 or less, which is like the Milky Way and the Large Magellanic Cloud. For more massive systems, people do merger counts, and I don't remember the reference offhand. But yeah, for larger systems which are easier to see, there are statistics, and you can, but I still think most of the numbers that people quote are coming from merger trees from simulations, actually, because we don't know. Yeah.
So you had a pie chart which basically shows 4% of the matter is just normal matter, 20% or so is the antimatter, and then 74% is the dark matter.
Yeah, I knew what you meant. Yeah.
How has that pie chart evolved over time? I mean, since when do we know that you now have, say, 70% or so, 20% or so? I mean, what would the chart look like in another billion years or 2 billion years?
Oh, so the evolution of...
Right.
Oh. I'm imagining the plot. Doesn't the... So the weird thing about dark energy is it seems to become more dominant as the universe expands. And so a lot of people, the sort of metaphorical way to think about dark matter is that it's the energy of the vacuum. It's the energy of space, and in particular of empty space, because it doesn't seem to care about whether there's dark matter or normal matter associated with it. So as the universe continues to expand, the relative fraction of dark energy to these other things is actually going to get bigger. And another way to phrase that is that it seems right now that the universe is going to expand forever to some degree of certainty. It all actually still overlaps a little bit in the true error bars, but that's a very schematic way to think about it.
This will be our final question. We can come up to the front.
Yeah.
The 74% dark energy relatively, couldn't it be just like, when you're surfing, there's a rip wave coming in, and that there's a wave, and that's the energy reading, and behind the wave there isn't nothing pushing it, it's just a rip wave coming in. So that it actually isn't 74%, it's just empty space behind the rip wave dark energy.
The impulse, right? Yeah.
Like
So
if something exploded out and everything's being carried by that, something you can't see, an energy, field that you can't see, so that it actually isn't really 74%. You just can't measure it behind the wave.
If the wave would not be accelerating, the expansion is.
yeah. What if we're just seeing the front of the energy coming from the Big Bang, and we're not actually seeing?
If there's something feeling behind.
Yeah. That it's so the acceleration part of the universe of that Adam Rees found is reasonably a good indication that we're not just seeing the shock front, because we're actually seeing this back through time to a significant fraction of the age of the universe. And we actually get measurement here of these same parameters. So you can measure this energy budget two ways. You can go out from where we are now, or you can measure it here. So working outward is what we call the near solution, and working in the C and B space we call the far solution, because this looks very far away. And it's there's tension now between those different measurements at the 2 sigma level, so 2 standard deviations. And that's not enough for the riptide effect. It is enough to say that we might be missing particle species. So some of the work I'm doing now is actually using galaxy halos, which, like I said, are these fossils. Things aren't changing very much in them. They're all very old stars and things like that, to actually measure the cosmic expansion rate. Because out in the halos, we're not influenced by a lot of the systematic factors that could be driving the difference between this, the sense of the universe we get from this, and the sense of the universe we get from not quite this data set, but to make it, actually, where is it? Yeah, so we can measure it sort of looking out this way, or we can measure it here. And like I said, an intervening space that we don't know exactly what's going on. So what we're trying to do is we're trying to make a measurement looking out that is as careful as possible to see if the differences between what we measure here and there actually persists. So I think, because we're looking at the universe at different times, and we actually have the universe at early times frozen in. This is at 300,000 years. That I don't think we could be seeing a shock front or a riptide. But there are things that we're trying to understand yet.
Okay, let's thank our speakers.